Okay, welcome to week 1, part 2 of the Intro to Programming with Python course. In the first lecture, we took a little bit of a background about Python. We also saw how to access Python by starting the idle integrated development environment. I already have idle running here on my screen. By default, idle shows a shell to which you can type Python code, and the shell will execute the code and display whatever result the code produces. We saw how to create variables by using the assignment operator to assign the variable to refer to a value. So we had things like FAHR for Fahrenheit gets 85, let's say. And we also introduced the idea of comments, which go from a pound sign or sharp sign to the end of the current line. Okay, I think I spelled Fahrenheit correctly there. Okay, so this statement is going to create a variable named Fair that is referring to the value 85, and I have some documentation describing that, which if I had typed out Fahrenheit as my variable name, I wouldn't really need the documentation. We then talked about using conventional arithmetic operators, the multiplication and division operators, star and slash, and the addition and subtraction operators, plus and minus, to do computations on values. So, for example, we have Celsius is 5/9 times the Fahrenheit temperature minus 32. All right, so that computation computes the Celsius temperature corresponding to a Fahrenheit temperature of 85. All righty. We also looked at using parentheses, as illustrated in this little example, for overriding or clarifying the usual associativity and precedence of these arithmetic operators. So here in week 1, we're going to take a look at some more arithmetic operators that are perhaps somewhat less used than multiplication, division, addition, and subtraction, but are nevertheless important and powerful and widely used, or at least used for their special purposes. We're also going to introduce what are called data types. You'll notice that in this little example I've typed so far, I have some integer values like 85, 5, 9, and so on. The result of this computation has a decimal point in it. That's what's called a floating point value. All right, so onward ho. The next operator we're going to introduce is the exponentiation operator star star. If you have a value followed by star star and then another value, x star star y, that computes x to the power of y. So if I say 10 star star, well, let me use just 2 to begin with, that computes 10 squared, which is 100. 10 star star 5 is 10 to the 5th power, which is 100,000. I can compute 2 to the 100th power. Now that's a big number. If you're not familiar with programming, it may not surprise you that we can do this. I'm not going to attempt to figure out, okay, so here we have the thousands, the millions, the billions, the trillions. I'm not going to try to figure out whether that's, nonillion or what that number is. But Python is able to compute 2 to the 100th power and display an accurate result for me. Many other programming languages are not able to do that using integer values. If I attempted to compute this number in C or C++ or Java or C#, I would end up getting what's called an overflow, and that would be an error. Now, the star star has higher precedence than multiplication and division, which in turn we talked about have higher precedence than addition and subtraction. And another thing that's peculiar about exponentiation compared to the other four arithmetic operators we've introduced so far is that exponentiation associates, from right to left. So if I were to say 2 star star 3 star star 2, this is valid. We're saying 2 to the power of 3 to the power of 2. And if we attempt to evaluate that as though it were something like multiplication or addition, we'd be tempted to say 2 to the third power. Well, 2 to the third power is 8. And then 8 squared would be 64. But actually what we get is 512 as the answer or the result of that computation, because exponentiation associates from right to left. So there are implied parentheses, if you will, around the 3 to the power of 2 part. The 3 to the power of 2 part is evaluated first, and then the result of that is treated as the exponent, and 2 is raised to that exponent. All right, so 3 squared is 9, and therefore 2 to the 9th power, well, you might not know that off the top of your head. The more you get into programming, the more you will start recognizing some of these powers of 2. For example, 2 to the 10th power, well, let me just hit the enter key to see the result here, that this is 512. 2 to the 10th power is what in computerese is called 1K. It's not exactly 1,000, but it is a power of 2 that is pretty close to 1,000. All right, so 2 to the 10th power is 1K. 2 to the 20th power is 1 megabyte, 1 meg, which is actually 1,048,576. 2 to the 30th power is 1 gig, and so on and so forth. So 2 to the 9th power is going to be half of 2 to the 10th power. All right? So 2 to the 10th power is 2 multiplied by itself 10 times. 2 to the 9th power is 2 multiplied by itself 9 times. And that's half of 1024, so that's 512. Okay, now here we have an expression that we've written as 3 times 2 star star 4 minus 2. And it looks, from the spacing that I have around these operators, as though I'm trying to compute 3 times 2 to get 6, and then take 6 to the power of 4 minus 2, which is 2. So in other words, I'm trying to get 6 squared, which is 36, out of this. But Python doesn't care at all about the spacing or lack of spacing that you put between arithmetic operators and values. And so when I hit the enter key, I get something that's, definitely not 36, because the exponentiation has the highest precedence among these operators. All right, exponentiation has the highest precedence, then multiplication has the next highest precedence, and subtraction has the lowest precedence. So what's actually being done here, regardless of my spacing, is 3 times 2 taken to the 4th power, and then all of that minus 2. Well, let's see. 2 to the 4th power, that's 4 times 4 is 16. And 3 times 16 is 48. Finally, 48 minus 2 is 46. So we get 46 from that arithmetic expression, regardless of the fact that I've used this spacing to try to indicate what I want to have happen. Python simply applies its precedence and associativity rules without regard to my spacing. If I want to force the multiplication and the subtraction to happen prior to the exponentiation, then I can put 3 times 2 in parentheses, and then give my exponentiation operator, and then 4 minus 2 also in parentheses. This will force 3 times 2 to be computed to get 6, 4 minus 2 to be computed to get 2, and then 6 to the power of 2 will be 36. Okay, so that's exponentiation. Next up, we're going to take a look at the unary plus and minus operators. Now, when we wrote expressions like 10, come here, there we go. Got to get my cursor in the right place. All right, so when we wrote things like 10 minus 5, this is a binary subtraction operator, binary minus. It has a value on the left and another value on the right. These are referred to as the operands, the left-hand operand and the right-hand operand of this subtraction. And I compute 10 minus 5 to get a result 5. Now, it is possible, though, to put a minus sign or a plus sign immediately in front of value, and that will be treated as a unary, or a single operand, in this case, minus sign. If I say 10 minus 5, well, minus 5 causes the 5 to be treated as a negative value, and if I say 10 minus a negative 5, that actually is equivalent to saying 10 plus 5, if you will, and I get 15 as my result. Okay? The unary minus sign has a higher precedence than multiplication, division, addition, and subtraction. It does have lower precedence than exponentiation, which is a little bit strange. By the way, you can also use a unary plus symbol. If I say plus 5 minus plus 10, well, this is a positive 5 minus a positive 10. That's going to give me a negative 5. In real life, in my experience, you will never see anybody use a unary plus sign on a numeric value, because for any kind of numeric value, plus n is exactly the same thing. Well, I should be writing this as a comment. Let me write it as a comment. Plus n is equal to n. So basically nobody uses the unary plus, and it's kind of in there for symmetry with the unary minus. The unary minus is used quite often. All right. So because of this strange fact that the unary minus has lower precedence than exponentiation, when I write minus 5 to the power of 2, once again, despite my spacing, which makes it clear what I'm trying to do, Python's precedence rules cause this to be evaluated as minus 25. That is, it's being evaluated as the negative of 5 to the power of 2. All right, so 5 to the power of 2 is computed first, and then I get the negative of that result. If I want to force the negative to be applied before the exponentiation, I therefore need to put the minus 5 in parentheses, and then raise that to the power of 2 to get 25. All right. So, another arithmetic operator that turns out is on the same level of precedence as multiplication and division is something called the modulus operator, the percent sign. And what the modulus operator yields is the remainder after division of the left-hand side by the right-hand side. So if I say, let's say 7 mod 5, well, 5 goes into 7 exactly once, and then there's a remainder of 2. So 7 mod 5 is 2. 22 mod 5. All right, well, 5 goes into 22 4 times with 2 left over, so there's, again, a remainder of 2. 12. These values I'm making up all have remainders of 2. So from the notes, we have 12 mod 5, which has a remainder of 2. I promise it's possible to get other values. For example, if I say 7 mod 6, of course, I'll get a 1. If I say 7 mod 4, I'll get a 3. The associativity and the precedence of modulus is the same as for multiplication and division. So if I say 3 times 5 mod 9, that's going to be evaluated as 3 times 5 first. Okay, we're associating from left to right. And then mod 9 is done after the multiplication. So the multiplication gives 15. 15 mod 9 is going to be the remainder, which is 6. If I wanted the modulus to be done first, then I would have to put 5 mod 9 in parentheses, 3 times 5 mod 9. Now 5 mod 9, 9 is greater than 5, so 5 mod 9 is just 5. And therefore we're computing 3 times 5 is 15. The fourth operator that's on that same level of precedence as the multiplication and division and modulus is something called floor division, which is 2 slash characters. What this does is to give you back the integer value of dividing j by k, where j is the operand on the left side. All right, so whereas modulus gives the remainder, floor division gives you the whole part of the division. If I say 12 floor divide by 5, well, 5 goes into 12 2 times with a remainder of 2, and I get the 2 that 5 goes into 12 by. That's not necessarily such a wonderful example, because the modulus of 5, 12 modulus 5 is also 2. Let me try a different example. So if I say 14 mod 5, this is going to be 4. All right, so 10 over 5 would be 2 with a remainder of 4. Therefore, 14 floor divide 5 is the 2, the integer part of the value of that division. Now, floor division always truncates the value in the direction of negative infinity. So if I compute minus 12, we'll do the example from the notes here, by 5. Now, minus 12 divided by 5, going in the direction of negative infinity, to get down to the next value that would be evenly divisible by 5, what I get is a minus 3. All right, so how can I think about this? This is kind of strange. Well, minus 10 floor divide by 5 would be minus 2. There's no fraction part resulting from that. Minus 11 floor divide by 5, that's minus 2, and actually a little lower than minus 2, because it's also, it's 1/5 below minus 2, and so that gets pushed all the way down to minus 3. And then likewise minus 12 floor divide by 5, all the way down to minus 14 floor divide by 5. These are all minus 3. Actually, minus 15 floor divide by 5 is minus 3. And then when I get below that, minus 16 floor divide by 5, now I get pushed all the way down to minus 4. Okay. So here now is the complete collection of arithmetic operators. These are shown in order on a line-by-line basis from high precedence to low precedence. That is, The exponentiation has the very highest precedence. Unary plus and minus have the next highest precedence. Multiplication, division, floor division, and modulus are the next precedence level. And then finally, the binary addition and subtraction, binary plus and minus, are the bottom level of precedence. Most of these binary operators, the exponentiation, multiplication, division, plus, minus, these are all binary operators. Most of these binary operators are associated from left to right. But exponentiation is the oddball here. Exponentiation associates from right to left. You can override the precedence or associativity of these operators in a complex arithmetic expression by using parentheses. Now, I want to emphasize that this table showing all of the arithmetic operators and their precedence and associativity is something that you should have baked into your soul, if you will. It's something that you should absolutely know without having to think about it a lot, and certainly without having to use Google. This relationship among these operators in terms of precedence and associativity should be as automatic for you as multiplying single-digit numbers together. If I were to ask you, what is 5 times 7, I hope you would just say 35. I hope you would not have to do some kind of computation in your head or on a piece of paper to figure that out. If you are any kind of data analyst and you don't know the multiplication table instantly, that's just embarrassing. Likewise, if you are a Python programmer and you don't know the rules for these arithmetic operators, that likewise is just embarrassing, and it's going to make you slow when you're writing code or when you're trying to read other people's code. Many bugs in Python programs are a consequence of slightly incorrect arithmetic computations, and those slightly incorrect computations in turn are often a result of someone failing to understand some of these precedence and associativity rules. You will gain practice with these operators and with the precedence and associativity rules by writing code, doing homework assignments, and so on. But I advise you to bite the bullet on this table, write this down on a 3x5 card, and check it periodically, let's say on a daily basis, until you know this stuff absolutely cold. That applies to other facts and rules as well. For example, the rules for what constitutes a valid variable name. But this is a particularly important table to understand completely. Okay, well, that's enough for now of me being the malevolent professor, so let's move on to the next stuff. Every expression that you evaluate in a Python program, such as the arithmetic expressions we've been working with so far, has both a value and also a data type associated with it. So for example, if I say 15 divided by 2, I get a value of 7.5. If I say 15 modulus 4, I get a value, a remainder after division of 3. The value 7.5 has a data type of float. Okay, that is, it's a value that has a fraction in it, a decimal point followed by some digits. The value 3 here, without the decimal point, is an example of what's called an int value. The data type in general determines how the value is stored in the system, that is, how much memory it takes and what the pattern of bits is that represents that value in the system. The type also implies how you can use that value in some other expression. And we'll talk more about that idea as we move along. All right, so these two digits, 1, 2, that represents the integer value 12, and it has a certain size and a certain pattern of bits in the machine. The value 12.0, on the other hand, Mathematically, that's the same value, but internally within the system, it's stored in a different way because it has to keep track not only of the decimal, the integer part, the 12, but it also has to keep track of a fraction part, which occupies a different collection of bits in addition to the integer part of the value. Now, the fact that the fraction part is 0 here does not alter the fact that this pattern of bits has to be stored in a different pattern than the integer value 12. Okay, and so for numerical computations, it's particularly important to be able to tell the difference between int values, integer values, that never have a fraction part, and float values that do have a fraction part, although that fraction part may very well be 0. For example, if I compute 2 to the... Earlier I computed 2 to the 100th power. Now here I have an integer value raised to an integer power, and I got this big number. I can actually compute using int values in Python 2 to the 10,000th power. Now that's a truly monstrous number. It goes flying off the top of my window, and if I scroll back, it's even hard to scroll. Idle gets very upset when it has to deal with this amount of output representing a number. So, I mean, you can see that this integer value, which is accurately displayed, goes on for, a few dozen lines. So that is a big, valid, correct int value. Python is able to store what are called arbitrary precision int values. However, if I compute 2.0 to the 10,000th power, 2.0 is a float, and even though the fraction part is 0, it's not valid, it turns out, to try to compute 2.0 to the 10,000th power as a floating point number, because in the format that floating point values are represented in the machine, that value is too big to fit. So I get yelled at. I get this red error message from my Python shell, and this overflow error, result too large. So int values and float values both represent numbers. Ints have the advantage of being able to represent arbitrarily big or arbitrarily negatively big, if you will, integer values to, thousands or even millions of decimal places. On the other hand, an integer value can never have a fractional part. Floats are able to have fractional parts, and they're able to represent values that are very tiny in magnitude, like 10 to the minus 100th power kind of thing. But the overall range of values that will fit into a float is more limited than the overall range of values that will fit into an int. So you have this trade-off that exists between when you want to use int values and when you want to use float values. All right, so as I said, an int value in Python 3 is represented in arbitrary precision. It's only limited by the amount of memory that you have on your machine, really. For computational efficiency, real numbers in the system are represented in 64-bit or 8-byte patterns referred to as float or floating point values. The range of values for a float is roughly between 10 to the minus 308th power up to 10 to the 308th power. And in terms of decimals of precision, we are able to store about 15 digits of precision. For example, if I compute a number like 1/3, 1 and 3 are both integers, but the division there is going to produce a float which will be 0.333 and so forth. Now the 3 ought to be a repeating decimal place, but it can only be displayed out to a certain number of positions. It can't be displayed infinitely, obviously. If I display some number like 5/12, now that last digit that's being displayed there, it may appear that that's rounding up, but you can't really know that for sure. All you can assume is that that last digit displayed is some kind of garbage, and the garbage may or may not be close to the actual value produced by that division. Now, irrational numbers like pi and e and the square root of 2 and so forth, again, can only be stored out to 15 or 16 digits because we only have a finite amount of space to contain those digits. So you want to think of a float as a reasonably close approximation of some real number within some range of restricted magnitudes. By the way, if I do compute something like 10 to the minus 308 power, this displays using the letter E to indicate an exponent. So 10 to the minus 308th power is displayed as 1 E minus 308, which you should interpret as 1.0 times 10 to the minus 308th power. Okay. If you have a variable stored in a value, I said that backwards. If you have a value stored in a variable and you want to know the data type of the thing that that variable refers to, you can use the type function to discover that type. For example, if I say type of 2, I get told that that is an int value. If I say type of 2.0, I get told that that is a float value. If I ask for, let's say I compute x gets 2/7, and I then ask for the type of x, I get told that x is referring to a float value, because when you divide 2 by 7, you get a float representation out to 15 or 16 decimal places. Okay, and as I said, you should assume that that last digit is basically garbage. All right, so here are generally the rules when we combine the arithmetic operators with the int and float data types. It turns out in Python that division, I should say in Python 3, that the division always yields a float, no matter what. So if I compute 2/2, well, 2/2 should be exactly 1. It is exactly 1, but it's not represented as an integer 1. It's represented as a float 1.0. 7/2 is 3.5. 2/3 is 0.666, etc., etc. Notice that in this case, the last digit shows as a 6. It's not being rounded up to 7. And in fact, even if I divide by 1, if I say 9 divided by 1, that is going to give me a float result, 9.0. Now, as far as the other operators, the other arithmetic operators, if both of the operators are int, if both of the values are, I'll get this right, if both of the operands are int, then the result is int. So if I say 2 times 3, and 2 and 3 are both ints, I get an int. If I say 2 plus 4, both are ints, I get an int. 2 minus 6 gives me a minus 4. Those are all ints. 2 to the power of 4. These are both ints, and the result is an int. One exception here is that if I have an exponent that is negative, a negative exponent is the same, really, as doing a division. So 2 to the minus 4 power, that's the same as 0.5 to the 4th power. And so that is a float, 0.0625. If one operand is a float, then the result is going to be a float. Again, regardless of what those actual float values are. So if I say 5 divided by 1.0, well, that of course is a float because I'm doing division, but if I say 5 times 1.0, I get a float result. If I say 2 to the 100th power, I get this big int value, but if I say 2 point to the 100th power, I get a float result. Or if I say 2 to the 100 point power. The existence of the decimal point in the number makes that value a float, even if I haven't specified a fraction after the decimal point. So again, same thing, I get a float result rather than an int result. All right. So that gets us to the conclusion of our introduction of the remaining arithmetic operators and also the two most common data types when you're doing arithmetic, either int or float, as well as using the type function. And Lab 1.2 will give you some practice and experience with this information.